You know, I wonder if I should stream the recitation, because I technically can. But I think that would just discourage people from coming even more. They'll just be like, I can just watch from home. Like, what's the point of showing up? Okay, so I think I'm just going to announce this at the beginning. I think there's a typo on the homework. It says, I need to confirm with Davi, but fall 2015 makeup doesn't exist. All right. And fall 2015 makeup number 2, even if you did the fall 2015 exam and you did number 2, it has nothing to deal with what we're doing right now. So what you want to do is you want to do the 2014 one. So I think that's the last problem on your homework.
For both of them? Like, are there 2 questions from them?
There's only one, I think. It's like spring 2016 and then something else 2016. Yeah, so that one doesn't exist. Okay, so hopefully this is enough chairs. Do we need to get the blinds here? I think you got it. Alright, we'll deal with this chair situation if we have to later. Just do this for now. See if we can figure out how to move it. Alright, so let's get started then. It's 9:01. Okay, I'll hand back exams at the end. And so this week, I'm going to be covering basis in class in recitation. That's because I think it's just something important to understand conceptually. Davi is moving on. He's skipping 4.7 and 4.9 for now, and we're moving on to 6.1 in class, which is linear transformations. After we do those, we'll come back. I think it makes sense because they're essentially like 4.7 is essentially a special case of a linear transformation, et cetera, et cetera. So yeah, and it's not on your homework this week, but it's still important to know what linear transformations are. So, all right. So plan for today, we're going to start off with linear independence for a little bit as a quick review, because that will motivate then the rest of the basis stuff. So okay, so let's do that. Linear independence. All right, and we'll try to do this stuff kind of quickly, but it still took 15 minutes last class. So definition of linear independence is that your vectors v1, v2, all the way through vk are linearly independent if the only solution, if the only solution to C1v1 plus C2v2 plus CKvk equals 0 vector is C1 equals C2 equals CK equals 0. Right, so this should seem familiar. That's just the standard definition of linear independence. In other words, i.e., what we can say then is, okay, the null space of this matrix where we put v1 in the first column, v2 in the second column, and vk in the kth column, right? If the null space of this matrix is trivial, all right, and I like this last explanation a little more because it's literally how you show something is linearly independent versus the first one, which is just a bunch of like letters thrown at you. Okay, so all right, so for example then, this is the midterm problem if you have 1, 1, 0, so V1 is equal to 1, 1, 0, V2 is equal to 1, 0, 1, V3 is equal to 0, 1, 1. All right, so you want to see if these are linearly independent or not. Question mark. What we want to do then is, okay, we're going to throw these into the matrix, right? And just like we said above, we'll throw V1 into the first column, 1, 1, 0. We'll throw V2 in the second column, 1, 0, 1. And we'll throw V3 into the last column, 0, 1, 1. All right. And so remember what we're trying to do when we're trying to solve the try to find the null space, right? We're trying to find AX equals 0, and we're trying to find the x's, right? So we have the homogeneous system, and the solution to the homogeneous system then is our null space. And so technically we do have like an augmented matrix with some zeros at the end, but because they are just zeros, right, we don't ever have to write them out, because they'll always, when you do row reduction, when you do any types of row operation, they'll continue to be 0. So let's then, there are two ways to do this. Just do the row reduction method because it's 100% safe. It works in every circumstance. So, all right, we're going to row reduce this. This is 1, 1, 0. I'm going to 0 out the first column. So that's 0. And then I subtracted the first row. So negative 1, 1, 0, 1, 1. And then the last thing here then, okay, I want to 0 out the second column, bottom row. And so 1, 1, 0, 0, negative 1, 1. And this is 0, 0, 2. Okay, and so essentially here what I have then is here's a pivot, here's a pivot, here's a pivot. I think there's a seat at the end there. All right, and then remember, we're solving the homogeneous system, so we have these zeros at the end. And what this essentially forces is that, okay, well, right, and also we want to remember that, okay, C3 is that column, C2 is this column, C1 is this first column, right? So what this forces essentially is that it forces C3 to be 0, right, which then forces C2 to be 0, which forces C1 to be 0. Okay, and so we see that C1 equals C2 equals C3 equals 0 is the only solution. So it's linearly independent. All right, that's fine. A more formal way of writing it, and I think it's quicker, is that the rank is equal to 3, which is equal to the number of columns. And so this alone tells me that the null space is trivial. So if the rank is equal to the number of columns, the null space is going to be trivial, and that's essentially because of the back solving thing that happens. All right, and so yeah, this is linearly independent. Another way to do it, then, another way to do it would say the determinant is not equal to 0, so it's linearly independent. Right, because so determinant not equal 0 also implies that the null space of the homogeneous system, right, is trivial. But in some cases, like this next problem, we're not going to get a square matrix, so you can't take the determinant in every single case. So that's why I did the row reduction method. All right, any questions for this? This we should be all familiar with this. Linear independence of like tuples of vectors. So what we haven't really seen, or at least I haven't really done an example of, is what if my elements aren't tuples of vectors, right? So for example, determine if 1 minus 4x cubed, 2 plus 2x, and 1 minus x squared plus 2x cubed are linearly independent. Right, so now all of a sudden we're not really dealing with like tuples of numbers anymore, but we still have to figure out, like, wait, are these linearly independent or not? So, okay, so what can we do? Well, remember the definition of linear independence is that, okay, C1 times the first element plus C2 times the second element plus C3 times the third element is equal to 0. And we want to find what C1, C2, and C3 are. Right, so those are more or less the unknowns of our system. And in this above problem, we're able to put our elements into a matrix. And in the definition, I essentially said, right, we want to form this matrix and find a null space. So what we want to do here is we want to turn these guys into a matrix somehow. And so it's probably then good to write out the matrix the vector formulation, which is then the following. Right? So we have some matrix, we multiply it by some vector of unknowns, and we get the 0 vector. Okay, so what goes in that skinny column vector of unknowns? What are we trying to find? Yeah, the C1s, right? The C's. So C1, C2, C3 go here. Okay, and then we realize, okay, so C1, right, multiplies 1 minus 4x cubed. So in terms of this matrix, right, C1 will only ever multiply the first column. And so, like, just do the matrix multiplication out. So if you had, like, entries in here, right, C1 would only ever hit that first column of entries. So that means that I need to make that polynomial 1 minus 4x cubed, and I have to put it in the column somehow. All right, since it's only multiplying C1. And anyone have any idea how we're going to do this?
0, 0, -4.
Yeah. So that is the idea. So we want to put the coefficients in the matrix, and we have to have some order to put the coefficients in. So what I'm going to do then is I'm going to say, okay, the first row is going to be all constants. The second row is going to be the x terms. The third row is going to be the x squared terms, and the fourth row is going to be the x cubed terms. Right? It makes sense. All right, and then so now we need to take 1 minus 4x cubed, and then we need to put it in the column. And so to do that, so the constant term is 1. There's no x term. There's no x squared term. And then the x cubed term is -4. Okay? And then the same idea has to apply for the second polynomial. So how would that go into my matrix? Oh, I had a typo, or not a typo, but that's a plus, I think. Yeah, so it should be 2, 2, 0, 0. And then the last row, last column.
1, 0, -.
Yeah, 1, 0, -1, 2. Okay. So that's our matrix. So that's our setup. And the matrix we care about is this matrix right here. So now what we want to do, since we're determining if it's linearly independent or not, we got to reduce it. So I'm just going to rewrite it. Okay, and then, all right, so technically, remember that we're solving the homogeneous system, but the zeros don't really matter, so we're not going to write them down. So this reduces 1, 2, 1. I'm going to divide the second row by 2. I'm going to multiply the third row by -1. And then the last row, I'm just going to zero out that first column. Okay. And then we see that, hey, that last row will get killed by the second and third rows. Right? I can do the last row minus 8 times the second row, and then do the last row minus 6 times the third row. And then, so that gets me a row zeros on the bottom. that's fine because look, what do I have? I have pivot, 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 which tells me the rank is equal to 3, which is equal to the number of columns. And what does that tell me? Yeah, null space is trivial. And so it's linearly independent. Any questions? Yeah, so again, we do row reduction because you can't take a determinant of a 4x3, so it's the only way to do it. And yeah, this is just one example of when your elements are not tuples of numbers, when they're polynomials, and then we'll see what happens when they're matrices, like immediately right now. But if there are no questions, I'll move on. All right, so that was the linear independence review. Hopefully we realize that, okay, polynomials can be linearly independent as well. But now we're going to talk about bases. And so, okay, what are bases? Let's begin with the definition. A set of vectors v1, comma, v2, comma, some dots, comma, vk is a basis of a vector space big V if the following conditions are satisfied. The first one is that v1 through v2 through vk are linearly independent, and the second condition is that if v1 through vk span big V. So just like subspaces, right, where you had to show closed under addition, closed under scalar multiplication, when you have to show something as a basis, you just have to check these two conditions. All right. So a lot of the vector space stuff we're doing now is just checking conditions, and so basis, these two conditions are what you need to check. All right. So for example, let's do one. Should be a simple one. 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 is a basis for M2R. Okay, that's really not phrased as a question, but whatever. We need to see if these four matrices form a basis for M2R. And so by the definition of bases, we need to check two conditions. The first condition is linear independence. All right. Now we don't have a tuple of numbers. We don't have polynomials, but we have matrices. And so what I have to do then is, okay, well, this is still like C1 times this first matrix plus C2 times the second matrix plus C3 times the third matrix plus C4 times the fourth matrix equals 0. Right? So that's still what we're trying to solve. And we're still trying to solve for C1, C2, C3, and C4. All right, so now we need to put it in some big matrix. And then we have our vector of unknowns. And that's equal to the 0 vector. But now the question is, okay, I have like matrices, and I need to put matrices into another matrix, which like just kind of doesn't make intuitive sense. Kind of like matrixception here, right? When you put matrix into, okay, anyways. So how do we put a matrix in a matrix? Does anyone have any idea?
Just represent it as like A, B, C, D, like down, just like one vector.
Yeah. So that's the idea, right? So C1, right, is still multiplying this entire first matrix, right? So what does that mean? That means this first matrix has to go in the first column because C1 is multiplying the first column. Okay? And so, okay, we need to do that somehow. And the way we do it is, all right, so you take the 1, or you take the top left entry, you put it there. You take the next entry, you put it in the second row. You take the third entry, you put it in the third row. You take the fourth entry, and you put it in the last row. Okay, so that first matrix is 1, 0, 0, 0. I just didn't want to write the zeros out, but that's what it is. And then, so you get 1, 0, 0, 0 going down the column. Okay, and then for the second matrix then, zero, 1, 0, 0. Third matrix, 0, 0, 1, 0. And then for the fourth matrix, 0, 0, 0, 1. Is everyone okay with that? Right. So essentially what we did is we had to unravel these matrices and put them into columns. Okay, so what do we care about? Well, we care about this matrix right here. And is that linear independent? Yeah, I mean, we can just take the determinant here, right? It's a square matrix, and it happens to be diagonal. So the determinant's 1. So it's linearly independent. Okay, so we know that these 4 matrices are linearly independent because well, we just showed it there. So the next step then is to show that it spans. And to show that something spans, we want to see, okay, so the first thing you want to consider is consider the most general element in the vector space you want to span. Okay, so we want to consider the most general element in the vector space we want to span. What's the space we want to span? V, which is, what was V in this problem? M2R, exactly. So, okay, so we want to consider the most general 2 by 2 matrix. What does that look like? A, B, C, D. Right, so A, B, C, D. You can hold that chair and sit up there. Okay. I'm the top seat. So, yeah, so A, B, C, D is going to be the most general element. And it's because, look, we don't want to make any commitments to what our matrix entries are going to be, so we're just going to make them unknown, essentially. All right. So that's the most general element. And so now what you want to solve is C1 times this guy plus C2 times this guy plus C3 times this guy plus C4 times this guy is equal to A, B, C, D. And you want to see if there's a solution, right? Is there a solution to that thing? Okay, well, this looks very similar to whatever the hell we did up here. All right. I mean, it's the exact same thing, but the only thing that's changed is the right-hand side. So I can just write this down as, okay, so we can just, essentially, we can just take this 4 by 4 matrix of our unraveled matrices, and we can just take that and then make an augmented matrix, and then what do we put on the right-hand side? Yeah, A, B, C, D. And we just need to see if that's consistent or not. Remember, up here, our right-hand side is essentially the column of zeros, right? So I just don't write it since it's like kind of pointless to write a column of zeros since nothing's going to change when you do row reduction on them. Here, we have to put A, B, C, D on the right-hand side, and then we need to see if the system is consistent or not. And it's pretty clear that the system is consistent, right? Because there's a pivot in every column and every row. So yeah, system is consistent. So it spans. And in fact, you see that, okay, C4 is equal to D, C3 is equal to C, C2 is equal to B, C1 is equal to A by back solving. But that doesn't really matter because you just had to show that it spans. Okay, so we've shown that it's consistent and it spans, so therefore we've shown that it is a basis. Or we've shown that it's linearly independent and we've shown that the vectors span, so therefore it's a basis. Any questions? All right, so it's almost like if I asked you guys to give me a basis for M2R, like these four matrices up here would probably have been like your first like guess, right? If I said choose any basis, because I mean it seems to be the most simple. I'm just taking this one, I'm just moving it around all the entries, right? And yeah, so this is technically like the most simple basis for M2R, and so a definition then, if we call the standard basis, you can think of the standard basis as the simplest basis for a vector space. Okay, it's the simplest basis for a vector space, and let's take a look at some other examples then besides M2R. So let's say R3. Right? If you had to give me a basis for R3, what's the simplest basis you can think of? Yeah, exactly. So it'd just be then essentially like the x-axis, the y-axis, the z-axis, right? So 1, 0, 0, 0, 1, 0, 0, 0, 1. That's going to be the standard basis for R3. All right. How about P2? So P2, polynomials of degree 2 or less. Any ideas?
Same way, yeah.
What do you mean by the same thing?
R3.
Is 1, 0, 0 polynomial? Yeah, exactly. So yeah, so P2 would be 1 x squared. All right, and we kind of did this already. Kind of spoiled this already. When we did the linear independence of these polynomials up here, right? I kind of chose arbitrarily to make these the rows 1 x squared and x cubed, and essentially that's because I picked the basis for P3 in this case, right? It's the simplest one I could think of, so that's why I put it like that, right? So yeah, so for polynomials then, it's going to be 1x and x squared. Why is it not 1 plus x squared? That's the discussion we had on the board here. But why is this not the entire basis? Why is it 1 comma x squared? Yeah.
Because they all need to be able to vary independently.
Yeah, so they
like
yeah, exactly.
like if you multiply like the thing on the right in red by like a, then it would just be like a plus ax plus ax squared, which
Right.
isn't going.
Right, exactly. So you need each term on your like polynomial to have its own coefficient essentially, and so that's why you need like them independently. You can't have the guy on the right. This can be part of your basis, but then you just need more elements in your basis to adjust for it. So keep that in mind. So this for P2, this is the standard basis, and then for M2R, it's shown above. So those are then examples of standard bases. And I'm not saying that this can't be part of a basis. It's just not the standard basis. Okay, so basis elements can be anything. All right, I'm just going to erase that. So any questions here? All right. More definitions. Dimension. So dimension is then the number of elements in any basis for V. So the number of elements in any basis of a vector space. And examples then, right? The dimension of R3. Any ideas? 3. Okay, what about more generally, what's the dimension of Rn? Yep. All right, what about the dimension of P2? 3. All right, generally, what's the dimension of Pn? N plus 1, yeah. So be careful with the polynomials. You got this constant term. That's kind of a bugger. That makes you have the plus 1. So common mistake on an exam would then just be, oh, you thought the dimension of P3 was 3. Well, that's unfortunate, but keep that in mind. And then, okay, dimension, let's do M4R. Not M2R, M4R. Any ideas?
4.
Not quite. So dimension of M2R would have been 4, right? 16. All right. And the idea is, right, what's the standard basis? You take that 1 and you move it around in every entry of your matrix. And you have 16 entries. So what's the dimension of MNR? Yeah. Okay. Theorem. So I know a lot of definitions, a lot of theorems, but these all flow into some kind of story. We're going to use the definitions before to use this theorem. So remember how we showed 2 things for bases? Well, this is actually a really nice theorem. You'll use it a lot, so I'm going to star it. But essentially what it says is if the dimension of V is n, and you have n linearly independent elements of the vector space, then one, they automatically span. And 2, they form a basis. Okay, and the discussion we can have here is the following. So how do I know this? Well, the dimension of a vector space, so you can't have more vectors than the dimension in your basis, right? So let's think of R3, and if you give me, so let's say I had 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And you gave me a 4th vector, right? Well, I can create that 4th vector from these 3 that I already have, right? So then, okay, so 4 vectors can't be linearly independent, so that means I need to have 3 linearly independent vectors, so that's n of them. but then I can't have less than 3 linearly independent vectors, right? Because let's say I took a vector out of R3 up there, right? Then I wouldn't span, right? So essentially, if I took 0, 0, 1 out, I don't have the z-axis anymore, right? So there's no way I'm in 3-dimensional space without a z-axis. So the idea then is, if you give me 3 linearly independent vectors, they're gonna be, so you know they're linearly independent, but then they have to span because any other vector you give me can be already formed by the previous 3, right? And then that being said, we satisfy the conditions. So really quick example for this one. Let's take R2, right? And so the dimension of R2 is equal to 2. And then you'll see that, okay, hey, 1, 0 and 2, 7. Okay, here's 2 vectors. They're linearly independent. By inspection, right, there's no way you're going to be able to reconcile those 2 vectors to be linearly dependent, and then therefore they span R2, and therefore they form a basis for R2. Okay, any questions? Last thing, before we get on to some examples, is the following. So this is just a note, but the dimension of a subspace is going to be less than or equal to the dimension of the vector space containing it. And that should make sense, right? Because what was my definition of subspace? Well, it kind of like hand wavy, but I said it was like a smaller vector space inside a bigger vector space, and I put smaller and bigger in quotes. Well, this is what I mean by smaller and bigger. All right. So the dimension of the subspace is going to be less than or equal to the dimension of the bigger vector space. So it's smaller in the sense that it has lower dimension. The interesting thing here is that, hey, it's less than or equal to, which means in some case the dimension of the subspace can be equal to the dimension of the vector space it can be contained in. But if we think about that real carefully, that can only happen in one circumstance. When is the only time the dimension of the subspace going to be equal to the dimension of the vector space it's contained in?
The subspace is the vector space.
Yeah, the subspace is the vector space, right? So a vector space can be a subspace of itself because, let's just check the definitions. The vector space is closed under addition, duh, and it's closed under scalar multiplication, right? That's it. That's literally all we had to check. So equals occurs only when the subspace is the entire vector space. So for the purposes of this class, that's like never going to happen, right? We're never going to ask you to prove that the vector space is a subspace of itself. So almost always that's going to be less than. But I just wanted to point out the one case where it can be equals to. All right. So now let's move on to examples. So let's do this one. I'll do a homework problem for you guys, if I can find it. Okay, so it's up to you guys to figure out which homework problem this is. Okay, so you want to so this is example 1. Let W be the set of 2x2 matrices such that A12 is equal to 2 times A21. And we know that W is a subspace of M2R. So we want to show that C is equal to 1, 1, 2, 1, 1, 0, 0, 1, 0, 1, 2, 3 is a basis for W. Okay, so it's really tempting just to use the theorem I said before, right? Where if we know these are linearly independent, then they automatically span. The problem with this one is that we don't know the dimension of the subspace, right? So it could be 2. So we have to do it the old-fashioned way of showing linear independence and span. So linear independence. All right, remember how we did this? We had to unravel each matrix into the column vectors. So I'll unravel the first one, 1, 1, 2, 1, 1, 0, 0, 1, 0, 1, 2, 3. And remember linear independence then, we're essentially solving the homogeneous system, and we want it to be trivial. We want the null space to be trivial, but we don't have to write the zeros in always. I'm just writing it there just to show. All right, so we'll row reduce 1, 1, 0. Let's see, this. Okay, let's just do 1, 0, 1. And then I'm going to zero out the third row. I'm just going to move it to the bottom. And then we'll move the fourth row up. Okay, and then 1, 1, 0. This becomes 0, negative 1, 1. And then this becomes 0, 0, 3. 0, 0, 0. Pivot, pivot, pivot. Rank is equal to what? Yeah, 3, which is equal to the number of columns. And so it's linearly independent because the null space is trivial. Span. Remember what the first step of showing span was?
Like in general form.
Yeah, so we need a general element in what? In M2R or in W? W, right? We want to show that it's a basis for W. So we need a general element in W. What does that look like? Not ABCD. That would be M2R. Because we have a condition on W.
A, B, 2B, C.
Yeah, so A, B, 2B, and C, right? Because we know that A12 is equal to 2A1. And so this guy has to be 2 times that guy. Okay. So again, this is the subspace. This was a subspace condition. We needed to form a general element that satisfies that subspace condition. And then so now we just take our matrix from above, and we need to add in A, B, 2B, C as an augmented matrix. Row reduce, 1, 1, 0. This is A. We'll leave that there. Okay. Row 3 gets killed by row 2, like all of it. And then we'll move it to the bottom. 1, 1, 3, C. And then we'll reduce again. So 1, 1, 0. That's A. 0, negative 1, 1. Well, I did row 2 minus row 1. So this is B minus A. 0, 0, 3. That's row 3 minus row 2. And so that's C minus A. 0, 0, 0, 0. And the system is consistent, right? So consistent system, so it spans. what happens if it wasn't? How would I know it didn't span? What would need to happen?
3 zeros and like a curve.
Yeah. So if this guy were not 0, oops. Right, if that entry right there were not 0, then it would not span. All right, and then we would not have a basis. But since it does span, so then it's a basis. Okay? It's one of the finals problems on your homeworks. All right, yeah?
Could you also say that because you can move A, B, and C, you have 3 different dimensions?
So if you move A, B, and C,
Yeah, because those are 3 like independent like elements, so the dimension is 3 here. Is that a valid argument?
not really, because let's say your condition was A12 equals like -3 times A21, right? Then this coefficient would be a -3, but then it wouldn't get killed in this operation here, but it'd still be 3-dimensional, right? So you kind of have to do it this way.
Okay.
Yeah, with span, like you more or less have to do it this way. All right, another example, and we'll do this one quick. Okay, find a basis for the 3x3 skew symmetric matrices. Skew sim matrices in M3R. Okay, so we want to find a basis for the 3x3 skew symmetric matrix. What's step 1? Step 1 is to show that this is a subspace. But that's easy, and you guys have done this before, so we're going to skip here. And sometimes you don't have to show it. It depends on what the problem wording is. All right, step 2, all right, if we want to find the basis for a subspace, this is going to be a hard step right here, and it's to construct a general element of the target space. Right? So you want to construct an element of the space that you want to span. And so in our case, it's going to be the skew symmetric matrices. So we need to construct a general 3x3 skew symmetric matrix. And so let's think then, real quickly, if we think of all 3x3 skew symmetric matrices, what's like one thing they have in common?
Elements in the negative on the other side of the diagonal.
Okay, yeah, that's one thing. I was thinking there's a more obvious one.
Diagonal 0.
Diagonal 0, okay? So yeah. All right, diagonal 0. All right, and then the next thing is what Jaden said, is that, okay, if we pick elements on one side, the other side has to be the negative of the elements, right? But so what you want to do then, the idea is, okay, where can I pick elements that force other elements to be something else? So for example, like, I don't have anything right now, so I can just pick A right there, right? That's fine. But am I forced to have something be in another location? Right, remember what skew symmetric means. Negative A transpose is equal to A. Right, so now I'm forced to have this middle left-hand side be negative A. Right, that's forced to happen by my choice of A. Okay, and then the same idea, if I choose B, where am I forced to have an element? In the lower left, and it has to be negative B. Okay, and then finally, if I choose C, that has to be negative C. So this is how you construct general elements of different spaces. You just say, hey, can I just throw random shit here? All right. Am I violating anything? No. Okay. And then am I forced to choose something else based on my choice of that random thing in the first spot. So that's kind of how you do this. And all right, so that's how we construct target general element of the target space. Step 3 is to rewrite as a linear combination. And so what are my unknowns? Well, my unknowns of my matrix are essentially A, B, and C's, right, since they're all scalars. So I can rewrite this as A times 0, 1, 0, negative 1, 0, 0, 0, 0, 0, plus B, 0, 0, 1, 0, 0, 0, negative 1, 0, 0, plus C, 0, 0, 0, 0, 0, 1, 0, negative 1, 0. Right? So I essentially took the matrix in step 2, I just broke it down into a sum of these A's, B's, and C's. Okay? Are we good with that? And then finally, we know what our basis is. It's going to be these 3 matrices without the A's, B's, and C's. And so this forms the basis of our subspace. And what is the dimension of our subspace? 3. Right? We got 3 matrices in our subspace, and so the dimension is 3. Okay? And do I want to talk about this? Yeah, so a hypothetical extension, a hypothetical follow-up, and you'll see this a lot. Extend this basis to M3R. What does that mean? M3R has dimension 9. All right, that's a claim everyone's okay with, right? To extend this basis to M3R, we need to find a basis for M3R that contains these 3 up here. So we need to find a basis of M3R that contains those 3 elements that we found for the subspace. And by the theorem, this means we need to find 6 more linearly independent elements. Right? Because the theorem says, hey, if I have dimension 9, then I need 9 linearly independent elements, and then they automatically span. I have 3 of them. They're up here, right? And then I need to find 6 more. All right? And then what are the 6? I'll just give you 6 example. So these 6 are valid. So you can have 1 on the diagonal. All right, so here's 3 of them. Right? Because remember, I had zeros in the middle. I had zeros on the diagonal initially. And then we know that in M3R, you can't have zeros on the diagonal of your matrices, right? That's not every matrix. That's not every 3x3 matrix. And then the other ones, the other 3 you can do, just look up here at where you have the negative 1s and just make those a positive 1. So you can have it here, you can have it here, and you can have it, I think, here as well. And then so plus the 3 above. And this is a basis for M3R. Okay. Any questions? Yeah.
Was there ever going to be a case where you need to show the 3 matrices up there are unique?
No, because they're linearly independent, right? A basis is always linearly independent, so that's enough. Because if they weren't unique, they wouldn't be linearly independent. They'd be the same thing, right? Or do you mean like it's a unique basis for that subspace?
No, like each matrix.
No, you don't want it. All right, I have your exams, and If this last part went over quickly, it's being recorded, so you can revisit it again. Ryan, you- Yep. This is you. David. Is he still on? Oh, Grace. Yours. Okay, Brian's, Paulo, Constantinos. Nicholas, right? Do you prefer Nick?
Nick is,
Okay.
I wrote it.
All right. Oh, here we go.
Thanks.
You have to be gave me that podcast.
Your exam?
Yeah.
Yeah, I already. You can.
No, I took it and then I gave it back to him for like the regrade.
Oh no, I never got it back from
Okay.
Bobby. Did you get? Did your grade change though?
Not yet.
Oh, okay. Maybe he. Yeah, I think he might be. Oops.
I'll give it himself.
Yeah. You're gonna have to talk to him about it.
Yeah.
See you.
Yep.